Hey everybody.
How many subscribers?
Let's do a subscriber check. Let's do a quick subscriber check because I think I've decided what I want to do for my 100 subscribers. I want to do a day in the life, of Mr. Labyrinth.
You're gonna vlog?
Or a draw of my life. You know. What would you like? What would be more?
Day in the life.
Day in the life? Okay.
Or Minecraft multiplayer episode.
93.
Yes.
Wow.
7 more.
Guys, everybody go subscribe.
I'm gonna be number 100.
You're just saying.
I'm gonna be number 100.
So you're waiting?
Yes.
You don't get a prize or anything, you know that. Got it. Okay. So in section 3.6, what we're going to do is we're going to take what we learned in section 3.2 with substitution and elimination, and we're going to apply it to systems of 3 equations. Because I said at the beginning of this chapter that we could solve, a system was an equation with at least 2 variables, or sorry, a system was a set of at least 2 equations with at least 2 variables. And I implied that there could be more, but we never really talked about it. So today is what we're going to look at. We're going to look at when we could have more than 2 equations. Okay. Now, you don't have to write this stuff down. I just kind of want to preface the algebra with what this looks like graphically. Systems of 3 equations with 3 variables, they're usually called 3x3 systems. As long as it has 3 equations with 3 variables, they're usually called 3x3 systems. In general, to find a solution to any system of equations, you need as many variables as you have equations. So that means that if I have 4 different variables that I want to solve for, I must have at least 4 different equations. If I have 5 variables that I want to solve for, I must have 5 different equations. See, everything that we've done up until this point was I've got 2 variables, so I only need 2 equations to find the system. And we're talking about equalities. We're not talking about inequalities, we're talking about equalities. Now, what does this look like graphically? Well, it's actually 3-dimensional graphing. Okay? It's actually 3-dimensional graphing. Like, for example, if I wanted to, back when we started learning how to graph, we said, okay, I've got an XY plane, right? An XY plane. I've got a horizontal number line known as the x-axis. I've got the vertical number line known as the y-axis. But we were all 2-dimensional. We were all flat surface. Okay. What would happen if we did put and I can't remember. Some people draw it out like this. Okay. That is what's called a z-axis. You kind of have to visualize it a little bit because we don't have it. I wish I had a diagram of it, how it looked in space. But we have to visualize it as, okay, x is going left and right, y is going up or down, z is popping out at you, okay? Z is depth, going either backward into space or forward into space. It's hard to draw 3 dimensions on a 2-dimensional surface, right? So you're just going to have to visualize it here. I've got an x coordinate going left and right. I've got a y coordinate going up and down. And I also have a z component going front and back. So if I wanted to say the point like 2, 3, 1, right? And that's what it would look like. That's a point in space at 2, 3, 1. That's saying the x value is 2. The y value is 3. Okay, so we're right here right now. And then it pops out at us 1, right? So it would look like this. So it's like 1 unit out at us. Oh, geez, this is hard to draw. I should have picked a better point. Let's go -2, -3, +1. Yeah, this one's going to be easier. -2, -3, then +1 up at us. So it would come out 1 unit. So it'd be like up there. It'd be like, oh gosh, I'm horrible at drawing these things. And then up 1 unit. It's like there. Oh gosh, that's bad. Sorry about that. But what we have to visualize, it's hard to visualize a 3-dimensional, I think that's wrong. It's hard to visualize a 3-dimensional space, no longer a plane, 3-dimensional space on 2 dimensions. Now, I'm not really going to be asking you to graph these things, but I wanted to show you the context of what we're going to be doing in the algebra behind it, okay? So take a look here. These are examples of systems of 3x3 equations. I have 3 different equations, and I have 3 different, no longer points, but actual planes, no longer lines, but actual planes. Like if I took an equation in 2 dimensions, it would be like y equals mx plus b. That forms a line, right? If I took an equation in 3 dimensions, that forms a plane. It's no longer a plane, it's a line, okay? Or sorry, it's no longer a line, it's a plane. I'm defining a plane using 3 different variables. Now, we can still use those terms, consistent versus inconsistent, okay? We can no longer use the terms dependent and independent because it's no longer slopes or y-intercepts, so we can't use independent or dependent. But what we can use are the terms consistent and inconsistent. Because remember, consistent means it has a solution, and inconsistent means it does not have a solution. Like for example, these 3 planes here, would this be a consistent or inconsistent system? Inconsistent, because there's not all one place where they're all meeting. Is this consistent or inconsistent? Inconsistent. They all have to meet. They all have to converge. They all have to intersect, right? Because if I think about the solution to a system, it's where the 2 things will share points in common, right? So if I say 3 systems, they all have to have these things in common together at one spot. Like for example, this would be inconsistent because these 2 planes will not cross, but this 3rd one will, but that doesn't, help us at all. Is this consistent or inconsistent? Inconsistent. Is that consistent? Yes. And it's consistent at a point, right? It's consistent at one point. Is this consistent or inconsistent? It's consistent because they all intersect, but in this case, they're all intersecting at a line. So there's man, you could take a whole course in 3-dimensional graphing and the implications of, solving these different things in college, of course. But again, what we're going to be looking at is most often this, okay? That's the example that we're going to look at the most here. Actually, all. We're not even going to look at it. Just showing you the different possibilities that you could possibly have with these things. So what we're looking at here is 3 planes crossing and intersecting at one coordinate. Okay, identifying the exact solution from a graph of a 3x3 is nearly impossible, especially if you don't have some 3-dimensional graphing capability. Okay? However, you can use the methods of elimination and substitution to reduce a 3x3 into a 2x2, and then use what we learned in section 3.2. So let's try. Go ahead and write this down. So this is a 3x3 system. If I were to graph this 3x3 system, I would see 3 planes. The first plane is noted by the equation 5x minus 2y is equal to -3. Z is equal to -7. 2x minus 3y plus z is equal to -15. 3x plus 4y minus 2z is equal to 7. Okay, so the method that I talked about last slide was I'm going to take a 3x3 and reduce it to a 2x2. I'm going to take a 3x3 and reduce it to a 2x2 by way of elimination. Okay, now everybody follow me here. I'm going to say this is equation 1, equation 2, equation 3. What's the easiest? I'm going to use 2 of the 3 equations. What's the easiest variable to eliminate with? And which equation is it in? Which variable is the easiest to eliminate with, and which equation is it? Is Z in 2 or 3? Good. Well, let's say Z in the second, right? You see Z in the second equation, it's alone. So let's use 2 and 3. Let's use equations 2 and 3. Okay? What I'm going to do to eliminate Z in equations 2 and 3, well, what do I have to multiply equation 2 by to make Z eliminate? 2. So here's the notation that I'm going to use. I'm going to say 2 times equation 2. Okay, 2 times equation 2. That yields me 4x minus 6y plus 2z is equal to negative 32. The third equation, now I'm just going to use plain old equation 3. Equation 3 is just 3x plus 4y minus 2z is equal to 7. And I'm going to eliminate z. Let's see what happens. Okay, well, that gives me a 7x minus 2y is equal to negative 25. Everybody following me there? Now, I used equations 2 and 3. Could I have used equations 1 and 2? Yeah. So let's do that as well. Let's use equations 1 and 2. Now, 1, I'm just going to take straight up, nothing different. 5x minus 2y minus 3z is equal to negative 7. But again, equation 2 is the one that I'm going to multiply by. What am I going to multiply equation 2 by to make it eliminate with equation 1? 3. Okay, so I'm going to take 3 times equation 2. Okay, so that gets me 6x, a negative 9y, 3z, and okay, I've got 3 times 16. What would 3 times 16 be? 48? Negative 48. I add down, I get 11x minus 11y is equal to negative 55. Okay, do you see how, by way of elimination, I eliminated using one of the variables. I eliminated z first to yield me a simplified system from a 3 by 3 down to a 2 by 2. Here's my new system. 7x minus 2y is negative 25. 11x minus 11y is negative 55. Do you see how in the homework I tell you which ones to eliminate with first? The only reason I'm doing that, you can really choose to do whatever you want. I didn't need to do z, that was just the easiest route to take. I'm going to tell you because tomorrow when we go to check this homework, like when we go over this homework, my key is going to be using these. I eliminate y first, I eliminate y first, and I eliminate x first. So could you do the problem in a different way? Of course you can, but if you want it to match what I'm going to show tomorrow, go with that. All right, now at this point, I can solve by whatever means necessary. I think it might be easiest to use elimination. Do you agree? So let's use elimination to solve this 2 by 2. Okay, so that means, well, what do we want to eliminate with? You want to eliminate x's or y's? I don't care. I'm going to eliminate y's? Okay. Means I'm going to multiply the top equation by 11 and the bottom equation by, let's go negative 2 for the bottom equation. Remember, look for the LCM. The LCM between 2 and 11 is 22. So I multiply the top equation by 11. That gives me 77x minus 22y. And then I'll get my calculator out now. 11 times 25. 250 plus, or 275? Yeah, 275. So negative 275. All right. Now I multiply the negative 2 with my bottom equation. That becomes negative 22x plus 22y is equal to a positive 110. I'm going to add these two equations together. Okay, this is going to get me a 55x is equal to negative 165, which conveniently, when I divide by 55, negative 3. Right, 165 divided by 55 is 3. So negative 165 divided by 55 is negative 3. Okay, that means I can plug in negative 3 into one of my two equations. Doesn't matter. let's go to the top. 7 times negative 3 minus 2y is negative 25. Multiply the 7 and the negative 3 together. Negative 21 minus 2y is negative 25. I add the 21 over to the other side. Negative 2y is negative 4. So y is positive 2. Okay, we got 2 coordinates. We just need to find the third one. So let's go back to our original problem and say, okay, which one's the easiest one to put in? Well, looks to me like equation 2 is going to be the easiest one to put x and y back into. 2x minus 3y plus z. It was 2x minus 3y plus z. Was it negative 16 on the right side? Am I saying that right? Thank you. All right, now we input all of those into the equation. So we have 2 times negative 3 minus 3 times 2 plus z is negative 16. We say, okay, negative 6 minus 6 plus z is negative 16, so negative 12. So z is negative 4. That means my final answer, the one point where these 3 planes will cross in space, negative 3, 2, negative 4. That's my answer. That's fun. Again, the key to these are staying organized. Did we learn anything new here, other than the fact that what this means, like that it's three-dimensional, that we can have a z coordinate? Not really, not mathematically, not algebraically, right? All of this process is very similar to what we've been working with before. It's just now applying it from 2 equations into 3 equations. Let's do this one. I'm gonna let you go on this one for a little bit and see what you can come up with here. Let's do this. Man, I could really use anything I wanted here. What variable do you guys want to eliminate with? Want to do z again? Yeah, that's fine. Totally fine. So let's do z, and let's eliminate, just so we're all clear, because there's a couple different routes to take. Let's eliminate with equation 1 and 2, and then equation 2 and 3. You notice that the other option I could have done was eliminate with equations 1 and 3, then 1 and 2. I'll give you some time to work. You would be so surprised. You know what the main issue is? Like every time somebody comes and says like, Mr. Avi, can you check my work? I would say like 75% of the time, you wrote the problem down wrong. Check to make sure the problem is written down correctly before you go through all that painstaking work. Okay, did everybody get this system? Negative 5x minus 5y is equal to 5. Negative 5x minus 7y is equal to 3. The only deviation I would expect maybe is that this may have been the opposite signs. Like if you had multiplied by negative 1 to the bottom, that would have been a positive 5x plus 7y equals negative 3. That would have been fine. And actually, that would have made our life a little bit easier in the end, because now I have to multiply by negative 1 here, where if you did it the other way around, conveniently enough, it was already set up to eliminate. Okay, so I'm going to multiply this by negative 1. So this gets me a negative 5x minus 5y is equal to 5. And then this is a positive 5x plus 7y is equal to negative 3. And now we're back to where the other people are. If you had multiplied the negative 1 to the bottom, to the third equation. So this gets me a positive 2y equals 2. So y is 1. No matter how we did it, we should have got y is 1. Let's plug it back in to find x. So we've got negative 5 times x minus 5 times 1 is equal to 5. So negative 5x minus 5 is 5. Add the 5 over to the other side. Negative 5x is 10. So x is negative 2. And then we plug it in to find z. Which equation you guys want to go into? 2 or 3? Go to 2. 2x plus 3y plus z is 1. 2x plus 3y plus z is 1. So we say, okay, 2 times negative 2, negative 4, plus 3 times 1 is 3, plus z is 1. So this gets me a negative 1, plus z is 1, so z is 2. So my final answer is negative 2, 1, 2. How we do? We do all right? I will tell you, the more you stay organized with this, the better it'll be. Now, I get it. These problems can be a bear, especially if you drop a negative somewhere. Oh man. And I'll tell you right now, I'll have to triple check it, but I believe there's no decimals on the homework tonight. So if you're getting a decimal, you're doing something wrong. But just let me double check. Section 3.6, page 224, 8, 9, and 10. Yeah, there's no decimals. Okay. So if you get any decimals on the homework tonight, check your work there. I'll give you about 10 minutes to work on your homework. Why not? Oh, see everybody playing along at home? So long. Don't forget to subscribe.